Hello, students. Today we're going to be taking a look at a new chapter of material. Hopefully today you send in your Chapter 11 test. I did give you an extra day, and if you checked via your email, you noticed that I extended it because chances are half the test took about 30 minutes, while the other half took about another 30. So hopefully you get that emailed and or uploaded. I should just say uploaded to OneNote to make things a bit easier for everybody. But yeah, upload that as soon as you can to your individual OneNote quiz page, Chapter 11 test. So yeah, today is a new chapter. Now I actually happen to be in the section entitled Remote Chapter 14 already. The calendar is identical, but it will propagate from here, really beginning on the 15th today, in such a way where, well, a new chapter begins. So chapter 14, section 14.1. Let's take a look. So today we're going to be talking about inscribed angles. And again, there's the PDF up at the top there. Please feel free to click on that, open it up, and then print it off in advance. Some of you may have a question or concern as to how you can print things off. You can print this particular page off via the OneNote. If you go to the upper right corner, the three dots, and then print, that's one option. Or, of course, you can just click on the PDF that I've inserted here for you. Okay, so inscribed angles. An angle of a circle is an angle whose vertex is on the circle and whose sides contain chords of the circle. We say that angle DEF intercepts arc DF. The following theorems involve inscribed angles. So the first bullet is if an angle is inscribed in a circle, then the measure of the angle equals 1/2 the measure of its intercepted arc. Let's actually use the picture to our advantage here. Okay, so if an angle is inscribed in a circle, we're going to go ahead and call this simply x. It could be, a degree value very specifically that we can then interpret. Where if we then suggest or use it as it suggests, then the measure of the angle is equal to 1/2 the measure of the intercepted arc. Well, the intercepted arc in the picture that they portray here is simply arc DF. I'm going to label this arc 2x because, as it hopefully makes sense, if x is an angle, let's even say it's 30 degrees, then the inscribed angle is 1/2 the measure of the intercepted arc, which would be 30 times 2, or 60 degrees. Bullet number 2. If inscribed angles of a circle or congruent circles intercept the same arc or congruent arcs, then the angles are congruent. So I'm going to draw a picture for this, and I'm going to try to draw here using the ink to shape tool. And let's see if I can do this. Maybe just use the shape tool. That'll be easier to do here. Easy enough. Here's my circle. You guys can draw one as well. And then I'll go ahead and I'll draw in, let's say, in a similar way as we saw in the prior picture, to rays. Technically, these are secant segments that run through the circle. One is represented here, but let's draw another one. Let's say right here. I'm going to use a different color. There we go. Let's save this. Do depiction. Now what I've done here is I've tried to create a situation where the points are shared here and here on the circle by not just the two blue secant rays, but also the two green secant rays. Let's read the theorem again, and I'm going to use some letters to highlight what we're talking about, and moreover possibly some letters. If inscribed angles of a circle or congruent circles intercept the same arc or congruent arcs, then the angles are congruent. So let's say this happened to be, well, 2x again. Okay, it would then hold true that this angle here is half as big, it would be x. So would this angle here be x. And if we're in degrees, you could label that as such. And I think I said variable, but I could also assess this with numbers. So if both x's here and here are 30 degrees, then the arc that they both intercept or create would be 60 degrees, 2 times 30. Bullet number 3. If an inscribed angle of a circle intercepts a semicircle, then the angle is a right angle. Okay, so for this particular shape, and let me go ahead and move this over here, I'll do it as such. And there's my circle. Okay, so let's go ahead and identify now. Again, inscribed angle of a circle intercepts a semicircle. Here's my notation for the diameter of the circle, which we know cuts the circle in half. Inscribed angle, let's say as such, here. Okay. The points that are intersecting here, as well as here, and therefore this angle that's created here, particularly, will always end up being a 90-degree angle or a right angle. Okay, very important theorem and set of corollaries to highlight in our kind of initial analysis. Let's continue. Example, in the circle above, find the measure of angle DEF if the measure of arc DF is 28. Since, here's their explanation, angle DEF is an inscribed angle, so the angle is on the circle, and it has its sides here extending out in such a way that, well, angle X is the angle in question, while arc DF, which I've already noted as 2x, will be the intercepted arc. So the measure of angle DEF will be equal to 1/2 the measure of arc DF. And because we already know what arc DF is, it's 28, we can simply divide by 2 and we get 14 degrees. So again, angle DEF being half the size of the arc is simply 14. Number 1, in circle P, RS, which is chord, is parallel to TV. Now we haven't seen parallel in a while, so let's go ahead and mark the picture. Here's one marking and here's another marking. This is going to help us frame inside the circle aspects that may later lead to angle relationships to be noted. Number 1, name the intercepted arc for angle RTS. Okay, so as far as that particular angle, here's angle RTS. I'll mark it as such. If I were to go as far as to label it with maybe a letter X, and we talked earlier again about how the intercepted arc, in this case here, would have to be what? Well, it'd have to be 2x. And notice again how the arc is created. It's created thanks to how, as we saw earlier, the angle that's inscribed extends out in such a way where it touches the circle at both point R and S. So simply the intercepted arc is just arc RS. We may later discuss again how big that is, but right now we're just defining what the actual letters are. Number 2, name an inscribed angle. So there's a whole variety of inscribed angles here. We already know angle RTS is one example. We can go as far as to maybe also say angle RVS, just to make a connection to the second theorem up above. It should make sense then that because RTS, angle RTS and angle RVS share the same arc, RS, that angle RVS is also X. So it would be a connection back to theorem 2 if we wanted to draw that connection. There are other inscribed angles for sure. We also have angles, for example, RSV. We also have RST. Remember to put my angle notation there. So, and there's a whole variety of them actually. Right? We can go as far as to extend STV as an option, RVT, and so on. Next, is angle RQS an inscribed angle? Well, here's the problem with RQS actually. Point Q is inside the circle, and that technically doesn't go back to the definition of what an inscribed angle is, where it's, again, an angle whose vertex is on the circle. So this is no. Again, Q is not on the circle. Only inscribed angles, angles that are technically inscribed, can only be found when the vertex of the angle is on the circle. All right, moving on. In circle P, arc SV is 86, and the measure of angle RPS is 110. Okay, so we're using the same picture. I'm going to go ahead and on number 4, find angle PRS. So let me go ahead and mark things up for you here. We've got SV as 86. Okay. We can argue then this angle right here should technically be half of that. Okay. We also know that angle RPS is 110. Now remember the nuance of the RS segment being parallel to the TV segment? Well, this actually is more interesting now in the sense that we can highlight things like alternate interior angles as congruent. For example, angles like so. This is going to be a little bit more interesting with marking, but we'll do our best here. I will also, though, note that because we've got some segments here where they are intercepting the circle to create arcs, we can make some connections to, well, not only congruent angles, but congruent triangles. So we can go as far as to mark this angle as also half of 86, therefore this is also 86 degrees. Okay, and some things will start to unfold quite nicely from there. So if I continue, again, we're trying to find the measure of angle PRS. Well, we already happen to have 110 degrees in the triangle RPS, which I'm going to draw off to the side here. So RPS, this angle is 110. We know also that thanks to the symmetry here, we've got an isosceles triangle to assess, wherein we can say that this side is actually congruent to that side. So we can go as far as to also say that these angles, these base angles, are, well, congruent. So PRS, if I were to call this, let's say, angle Y, and angle Y, again, angles are congruent on an base angles are congruent on an isosceles triangle. We can find this by simply taking 180 minus 2, minus 110, and that should be equal to 2y. Now, in a different way, we can consider that 110 plus 2y is equal to 180. That's perfectly acceptable as well. Let's finish it up in this manner. We can say then that what? 7 equals 2y. The y, of course, is 35. And that's exactly what that angle PRS happens to be.